Welcome to Management 670. Today I want to spend a few minutes talking about measures of association. So let's get started. Measures of association are descriptions of how two seemingly different variables might have a relationship between one another. We call this correlation. We have a few examples down here at the bottom. If we think of x and y as two different variables, and they're measured and gathered, and when we plot them against one another with the x on the x-axis and the y on the y, we can see kind of a relationship that the two of them have right now. So in A, we can see a positive relationship. So as x is generally larger, y is generally larger. The reverse is true for B. When x is large, y is typically smaller. And the reverse, so when x is small, y is typically large. And finally, C shows a relationship, but it's not one that we describe through correlation. We would say they would basically be uncorrelated. The two don't seem to have a relationship or move in the same direction at the same time as one another. This linear measure is called covariance. And that linear is important because at no time did I discuss on the previous slide anything that was curved. These were linear associations. A seems to be from the lower left to the upper right, B from the upper left to the lower right, but C has no linear relationship between the two. So we say that relationships are positive or negative. Positive means same time or same movement direction, and negative is the opposite. One is up, the other is down, typically. Here's the sample covariance. So given a sample of data set, we see that we can calculate it by taking or finding the average of both x and y, so the mean, the sample mean for x and y, subtracting those values from the observed values, xi and yi, and then we divide by n-1 since it's a sample. For a population, very similar. This time we're dividing by the total sample size n, not n-1, and we're not talking about the sample mean, but we're talking about the population mean. So that's Greek mu for mu x and mu y. At the bottom, I've decided to include some Excel functions that are popular and very powerful when making spreadsheets. Covariances can be very large numbers, very negative or very large negative numbers. But for correlation, those are standardized. Now instead of an infinite range for covariance, we can make it on a -1 to 1 range. We take the sample correlation, to calculate the sample correlation, we take the sample variance, we divide by the standard deviation of x and the standard deviation of y. So for the sample, that's for the sample standard deviation, and for the population, that is the population standard deviation. That will force this relationship between -1 and +1. Again, Excel correl function can help with this in spreadsheet modeling. As I said, correlation now exists on a range from -1 to a +1. -1 being perfect negative correlation, and +1 being perfect positive correlation. There's of course a range, and the closer that number, whether positive or negative, is to 0, the less influence one variable has on another one. So anything that is perfectly positive correlated means they move exactly in sync in the same direction. Well, negative correlation means they move in opposite directions every single time. Here's some more examples. So R is the correlation coefficient, and something that is 0.8 shows a very linear positive relationship. Notice how the values are pretty tightly packed together in the upper left graph. Well, in R equals 40% or 0.4, still positive. It's still a positive relationship between these two variables, whatever they happen to be. But you can see the data values start to spread out a little bit until finally we get to R equals 0. And even though the values are kind of bunched up together, there certainly is no one line you could draw that would reflect that relationship. On the bottom line, we see a -0.8, so that's highly negatively correlated. -0.4 shows the same similar negative relationship between the two variables, but again, spread out a little bit more. And the lower right graph right there shows a nonlinear relationship probably between the two variables, but For a correlation, we would say that's about a 0.0 because this is a linear description of the two variables. A very common phrase is that correlation is not causation, and that is absolutely true. So for the next couple of slides, I want to describe some of the relationships, some of the different types of effects that appeal to correlation and the difference with causation. There's a Hawthorne effect, which states that individuals that know they are being evaluated will perform differently. There's a famous study about productivity where they adjusted the light levels on a manufacturing floor, and no matter if they turned the lights all the way up for very bright or very low for very dark manufacturing room, the workers worked harder. They knew they were being observed, so they put in more effort, kind of spoiling the results of the experiment. A little similar to the John Henry effect, in which the control group knows that it's the control group and therefore will work harder to make up for any perceived disadvantage. If a group of individuals receives the placebo and they know it for some medical test, then they will be more likely to state that they are performing better than had they not been known. The gambler's fallacy is one that believes that previous events will change the inherent probabilities of events happening. These are sports streaks or also a roulette wheel. Another common phrase is a regression towards the mean. While in the long run, there are statistical properties and properties of probability that say that that will be true, but on the short run, that is not true. A few extreme events can occur, but that doesn't mean that more moderate ones or more common answers or results will happen next. There's also a difference between an observed value and one that was gathered in some type of experiment. In an observational study, the data gathered can be thought of as a record. It's something that happened but wasn't in a controlled environment. For an experiment, usually the purpose is to try to find some type of influence, so it's specifically created. The difference is in recording something that happened in real life in an uncontrolled environment as opposed to one that was specifically created or in a controlled environment. Finally, for this slide, there's a fishing expedition where researchers jump from one question to another after failing to find some kind of success to prove some type of hypothesis. After failing multiple times, they just continue on, asking the next question and the next question. And now that's actually particularly easy to do because of big data. We have such large data sets and so many ways to gather data and analyze them that a fishing expedition can often be counterproductive to what the initial study was. Finally, the last slide of correlation versus causation techniques is sometimes there are co-occurring characteristics. These are when perhaps two different sources of variance, these two sources of influential aspects are involved at the same time, and they are not accounted for. There's the empirical generalization as well. This is sometimes known in philosophy as an ecological fallacy. It's where you ascribe an individual behavior based off of some aggregate statistics. It certainly is an important perspective to have, but care needs to be taken to state individuals acquiring any characteristic from a larger group. This can be thought of as a macro property given to some micro event. And finally, a very common bias that happens frequently in most of our lives is confirmation bias. It's where individuals give more weight to the information or news articles that support their personal beliefs. An example that's very common in the news is this ongoing discussion and fight about vaccines causing autism. Proponents of this theory search online and reject any of the controlled studies out there that contradict their current belief, but then they are quick to promote any study or article that supports what they already believe. In conclusion, we've now discussed several types of data, and now in this lecture, it was about how they relate to one another. Does X correlate with Y? The next step from there is to take care, but then maybe determine if there is a causal effect between them.